Alright, let's look at this example. We want to sketch the graph of this function f of x is equal to x squared plus 2 over x squared minus 25. Alright, so let's get some information from the original function f. The domain. Right, so you can see that if you set the denominator equal to 0, so you have x squared minus 25, which can be factored out as x plus 5 and times the quantity x minus 5, and we don't want this to be equal to 0. So which means that x cannot be negative 5 or positive 5. So we have to, we can say domain would be negative infinity to negative 5. And we're going to skip negative 5 and go to positive 5 and skip positive 5 and then go all the way to infinity, right? So that's the domain. So all real numbers except for positive 5 and negative 5. Alright, and x-intercept. So set y equal to 0. So we set the function equal to 0. But you can see that since the x squared plus 2, the numerator is never 0. So there is no x-intercept. So x-intercept, there is none. Alright, y-intercept is actually pretty easy to find because you just have to plug in x equals 0, so y equals f of 0. But if you do that, 0 squared plus 2 is 2 on top, and then you have 0 minus 25, so it's going to be negative 25. So y-intercept is 2 over negative 25, or negative 2 over 25, right? And a vertical asymptote is going to be, right, so there's no common factor on top and bottom, so we can set the denominator equal to 0, so you can see that x equals negative 5, and also x equals positive 5 would be vertical asymptotes. Alright, the trick to find the horizontal asymptote of the rational function is that you have top degree is 2 and the bottom degree is 2, which means that the y equals the leading coefficient of the top, which is 1, over leading coefficient of the bottom is 1. So horizontal asymptote is y equals 1 over 1, which is actually just 1. Right, so y equals 1 is the horizontal asymptote. Alright, then we're gonna get to the second derivative. So let's take the derivative. So this is going to be a quotient rule. Right, square the denominator. So quantity x squared minus 25 squared. Right, derivative of the top is 2x. Times the bottom, x squared minus 25 minus top is x squared plus 2 and times the derivative of the bottom is 2x. Right? So you can see that we can factor out 2x and 2x because that's in common. So you have a 2x. Right, but you can see that you have x squared minus x squared cancel out. So you have a 25 minus 2, so it's going to be negative 27. Right, then denominator is the same, so quantity x squared minus 25 squared. Right. And we can just multiply these numbers together. 2 times negative 27 is negative 54. So this is going to be a negative 54 x over quantity x squared minus 25 squared. Alright, so let's do a number line to discuss increasing, decreasing behavior. So I'm going to draw a number line. Alright, and then first we actually have to set this guy equal to 0. And to find the critical number, so you see that the numerator equal to 0, so negative 54x equals 0. But you can simply divide through by negative 54 to get x equals 0. So x equals 0 is the critical number, right? So I'm going to put a tick mark at 0. And also domain excludes negative 5 and positive 5, so we're going to put those two. So you have a negative 5 there, and then we have a positive 5 there. Right? Then we just have to look at the sign of first derivative f prime. Right? So we can try any sample number less than negative 5. So I'm going to try x equals negative 6. Right? Then you look at the derivative. So I'm going to look at here. Right? Then we know that the denominator is always positive because there's a square there. Right? So we just have to look at the sign on the top. So negative 54 times negative 6 is going to be positive. So I'm going to put a positive sign here. Right? Then we can try any number between negative 5 and 0. So I'm going to try x equals negative 1. Right? So you have a negative 1 times 54. So it's still going to be positive. So we have that. Alright, after that, between 0 and 5, so I'm going to try x equals positive 1, right? And negative 54 times 1 is going to be negative, so we have a negative sign here. Alright, then we can try x equals 6 here. So you have negative 54 times 6 is going to be, of course, negative. Right? So this tells you that function f is going to be, on this interval, you have increasing behavior. Positive derivative, again, it's increasing. Negative derivative, so it's going to be decreasing here. Negative derivative, it's decreasing here. Alright, so we have this increasing, decreasing behavior. Alright, then we can look at the second derivative. So we're going to have to take the derivative again. Right, first, I have a negative 54 is just a number. So I'm going to put negative 54 outside. Then we can just use the quotient rule for the rest of it. Right? Square the bottom. So you have quantity x squared minus 25. Raise it to the fourth power. Right? Derivative of the top is going to be 1 times the bottom, it's quantity x squared minus 25 squared, minus top is x, times the derivative of the bottom is going to be 2 times, keep the inside function as it is, and subtract 1, so it's going to be first power, then multiply by derivative inside, which is 2x. Right? Then we can simplify. Negative 54 is just a number, sits there. And the denominator looks good. So quantity x squared minus 25 to the fourth power. Right? And then we just need to factor out the common factor. So you have a x squared minus 25, and there are 2 of them on the first term. So I'll just pull out the one of them. So you have quantity x squared minus 25, right? And then if you collect the leftover terms, we have another x squared minus 25. So you have x squared minus 25 here, right? Then we have, there's going to be negative 2 times 2, so 4x squared. So we're going to subtract 4x squared, right? So we can cancel x squared minus 25 on top. So it's going to cancel one of them. So fourth power becomes cubed. Right, then if you clean it up, you're going to get this. Negative 54 times. Alright, so you have, let's see, x squared. So I took care of this. Alright, x squared minus 4x squared. So it's going to be negative 3x squared. And then you have negative 25. Oops. Negative 25. So we have that, negative 25. Alright, and then we have quantity x squared minus 25 cubed power. Alright, I'm going to just distribute the negative sign to both of these guys because both of them are negative, so it's gonna be positive. So you're gonna get 54 is a number, right? Then negative negative, so it's going to be 3x squared plus 25 over quantity x squared minus 25 to the third power. Alright, so we're going to do the same thing we're going to do a concavity analysis. So we have a number line. Alright, and then if you set this equal to 0, actually this guy is never 0. So we don't have a tick marks from there, but we still have to put tick marks for negative 5 and then positive 5 because functions are not even defined there. Alright, then we look at the second derivative, f double prime. Alright, so let's try x equals negative 6, just like before. Right, then we notice that here the numerator is always positive, so we just have to look at that. So it's a negative 6 squared would be a 36 minus 25 positive, cube is positive. So it's going to be positive divided by positive, so it's going to be positive there, right? And then you can try any number, so I'm going to try 0. Alright, if you try 0, negative 25 cubed is negative, so positive divided by negative is actually negative. And then we can try x equals 6 as a sample number. Alright, 6 squared, 36 minus 25, positive. Positive divided by positive is positive. Alright, so which means that if you look at the original function, right, then we know that the positive second derivative tells you that it's concave upward. Negative second derivative means it's concave downward. And a positive second derivative means that the original function is concave upward. Alright, so if we put all these things together, we can sketch the graph of the function f. Alright, so let's try to do that here. So here's the x-axis. Alright, and I'm going to put the y-axis right here. And we know that, let's see, there's a vertical asymptote at negative 5. So if you look at that, so vertical asymptote at the negative 5 and then positive 5. So let's put that. So here's negative 5. So there's a vertical asymptote there. Alright, so here. So vertical asymptote. And then at positive 5, you still have another vertical asymptote. Alright, so we put the vertical asymptote, then we tend to use the dotted line for that. Alright, and then we have horizontal asymptote is y equals 1. So this is negative 5 right there, and then positive 5. So 1 should be somewhere around there. So it's a 1. So there's a horizontal asymptote going horizontally, and so going like that. Alright, so this is going to be the horizontal asymptote. Alright, then let's follow this picture. So we have to, from negative infinity to negative 5, so on this interval, we have an increasing picture and a concave up picture. And we have a horizontal asymptote and a vertical asymptote. So we know that the graph should look somewhat like this, right? Increasing and concave up. All right, and then between negative 5 and 0, right? We have an increasing picture, but it's concave down. And also, if you look carefully, right, at this critical number x equals 0, doing a first derivative test, increasing turning into decreasing, so you're going to have a local maximum happening at there, and the value there is actually it's the same thing as y-intercept, so it's a negative 2 over 25. So if you put the negative 2 over 25, it's probably somewhere around here. So it's a negative 2 over 25. Then the graph is going to be, it's increasing but concave down. And then you have a vertical asymptote there. So increasing but concave down. So you're going to have a picture like that. And after that, it's going to be decreasing concave down, and you have a vertical asymptote at positive 5. So we're going to have a graph like that. All right, and on the last interval, you're going to have a picture decreasing and concave up. So you're going to have a picture like that. All right, and in this case, since the second derivative is never 0, so we know that there's no inflection point. But we would have here, this is a local maximum, and it looks like it's a local maximum here. So this is a local maximum there, but there is no local minimum. All right, that's about it. I hope that this was clear.